Assalamu alaikum students. Good evening to everyone. Am I audible to you all? Are you able to see the slide? Can anyone please confirm? Yeah, thank you. So before starting today's session, I would like to tell you all that the discussion board activity is already available on the Blackboard. I hope some of you are already posted your answer and still some students not yet posted. So please complete the discussion board activity by the due date which is given there. Okay. And one more thing regarding the content. So we will try our best to cover the content that we are lagging behind because still we are in module 2 and yet we need to complete module 3 and 4 as per the schedule. So we will try our best to cover whatever the possible content in today's class that we will go through, and the leftover content will be given as a recorded session by tomorrow noon so that we will overcome the delay of covering the modules, because day after tomorrow you will receive more assignment 1. So in the assignment 1 you will be having the content from questions from module 1, module 2, module 3 and module 4. So that is the reason I would like to give the leftover content. I mean, after today's class, whatever the leftover content is there, that will be given as a separate recording. Okay. So now, without further delay, let us continue with today's session. And I think I didn't share. Okay. Just give me a minute to share the slides. Okay, in another few minutes, you will receive a Blackboard message saying that the slides. So when you go to that message, you can download the modules, all the modules content, like starting from module 1 till module 13. I hope by now you all have received the message in your email, if I'm not wrong. So you can check your course message box if it is visible to you all. Um, you can try once to download the content. If anyone still not received, let me know. Okay. And also, can anyone confirm me whether you are able to see the message that I have sent in the Blackboard with the attachments? If not, I will send it again. Yeah, thank you. So from that message, you all can download the content from module 1 till module 13, all the week's PPTs I have attached in that. Why? Because I got a lot of emails and messages from the students saying that you have some difficulty to download the content from the Blackboard. Even I am also facing the same, but I don't know the technical issue, what is happening with the Blackboard. So that is the reason I have shared the content to you all through the message box. So I hope it is clear to everyone. Now, without further delay, let us start today's session. So in the previous session in this week, we learned about the various aspects and concepts related to the SHA family, including SHA-256, SHA-384, SHA-512. So now let us start understanding about SHA-512, which works internally. So SHA-512, which is the member of the SHA-2 family of cryptographic hash functions. So its main purpose is to generate a unique 512-bit message digest, I mean the hash value, from any input message. So let us say SHA-512 does not encrypt the message, right? So instead, it is going to create a digital fingerprint of the message, and in simple terms, I can say that SHA-512 can process a short text message, a short text message, a PDF document, a large database, and a video file. So there is no practical restriction for normal applications. So SHA-512 does not process the entire message at once. Instead it divides the message into 1024 bit blocks. So each block is going to be processed one after another. Imagine you have a very large book. You have a very large book with you, and instead of reading the whole book at once, what you will do, you will read like module 1, module 2, module 3. Similarly, the SHA 512 will process 1024-bit block at a time. So no matter how large the original message is going to be. So SHA 512 always produce a 512-bit message digest, and this output is called hash, message digest, hash value. So all the three terms, which means the same thing. Okay. So in the first step, it will append the padding bits. It will append the padding bits. Sometimes the message length is not exactly the required size for processing. So SHA-512 add extra bits, and that we call it as padding. So imagine, for example, you are packing some chocolates into the boxes. So each box must contain exactly 20 chocolates. If the last box contain only 18 chocolates, we will add two fillers padding which works the same way. Like extra bits are added until the message reaches the required format. Required format. In the second step, it will append the length. So SHA-512 perform another important step. It add the length of the original message. Why? Because two different messages could otherwise end with the same padded bits. So including the original message length will help the algorithm uniquely identify the input. Then in step 3, now the SHA-12 will prepare the processing. So it creates something called the hash buffer. So when you think of the hash buffer as a working memory that is used while calculating the final hash, initially it contains the predefined starting value, and these values are specified in the SHA-512 standard. So then now where we comes to the main calculation, each 1024 bit block is processed one after another. So the current block interacts with the current hash buffer, and the hash buffer is updated. The hash buffer is going to be updated. So what is the concept here? You can see the block 1 update the hash buffer, then block 2 update the hash buffer, then block 3. So likewise till the final block, the hash buffer will be updated. Every processed block contribute to the final hash value. If even one bit change anywhere in the message, the final hash changes dramatically. So this makes the SHA-512 excellent for detecting the modifications. So in overall, SHA-512 will accept a message. SHA-512 will accept a message of almost any practical size, and it will add the padding and the original message length so that it will initialize its internal hash buffer, processes the message in 1024-bit block, and finally it produces a fixed 512-bit message, a digest. So SHA-512 round. See, we now we know the major 5 steps that involve, like append the padding bit, append the original message length, initialize the hash buffer, then process the message in 1024 bit blocks. So whereas we will produce the final 512-bit hash value. So now the computation is going to be called when the SHA-512 processes 1024-bit block. It does not process the entire block in a one step. Instead, it processes the block through a series of repeated operations that is called round. That is called what? Round. So in the exam, they may ask like this. In SHA-512 process, a 1024-bit block processes the block through a series of repeated operations is called as dash. Then the answers may be given round, square, rectangle, something like that. Then you need to choose the answer round. So when you think of each round as a small processing step that gradually transforms the data. So like for example, imagine we used to wash the clothes using washing machine, right? So you do not simply put your dirty clothes into the washing machine and instantly get the clean clothes, right? Instead, what happens? The washing machine will perform several stages. First it will soak, then wash, then rinse, then spin, then dry. Similarly, the SHA-512 process every block through multiple rounds before proceeding the final hash value. So as you can see here, we have like a 0 less than or equal to t or less than equal to 17. This means the SHA-512, which performs 80 rounds. So for every 1024-bit message block, each round will update the internal state of the algorithm. So at the beginning of every round, the SHA-512 has an internal working memory which called the hash buffer. So together, these 8 values are going to form a 512-bit internal state, 512-bit internal state. So every round will perform the calculation using the 3 important inputs. One, the current hash buffer. Number 2, the message word. And number 3, the round constant. So that it will start operating the operations that performed in each round. Number 1, that will be a circular shift. Number 2, it will be like Boolean operation. And number 3, it will be like the complete round. So remember, these repeated transformations will ensure that even the smallest change in the original message will produce a completely different 512 hash, that providing strong protection for data integrity. So far we have studied the SHA family, especially we dealt with SHA-1 and SHA-2. So these algorithms are widely used to verify the data integrity and also to support the digital signatures. But the next generation of secure hash function, that is SHA-3, we have 2 other well-known hash functions. One is MD5 and Whirlpool. So the technology is constantly evolving. As the computers become more powerful, we have new attack techniques that are discovered. So to prepare for future security challenges, NIST, the National Institute of Standards and Technology, will be announced a competition in 2007 to develop a new generation of secure hash function. So the winning algorithm will become the SHA-3. So if you notice something here in this slide, the SHA-3 was not created because SHA-2 was broken. Instead, it was developed to provide an additional security standard with a different internal design. So this gives the cybersecurity community another trusted option. So the NIST defined several requirements for the new algorithm. So the first requirement says that SHA-3 should be able to replace SHA-2 with minimal changes. So this often called as the drop-in replacement. Suppose, for example, let us say there is a company who already use SHA-256. If they decide to move to SHA-3, they should not have to redesign their entire software system. Only the hash algorithm will change. Everything else will remain almost the same. Like imagine, for example, in your home, you want to replace a light bulb, and if the new bulb fit into the same socket, you simply remove the old one and install the new one. So you do not replace the entire electrical system, right? This is the same idea that we are using here in the drop-in replacement. So SHA-3 should process reasonably small blocks instead of storing the entire message in memory before processing. Like imagine you have a 20 GB of video file. It would not be practical to load the entire file into the memory. Instead, the SHA-3 processes the data gradually, making it more efficient for very large files. So MD5, which stands for Message Digest 5. It was developed by Ron Rivest, the same cryptographer who designed RC4 and co-developed the RSA algorithm. So MD5 always produce 125-bit hash values. So a 120-bit hash value is considered too small for many modern security applications. But the researchers discovered practical method to create coalitions in MD5. That means different messages can sometimes produce the same MD5 hash value. Because of this weakness, the MD5 is no longer considered secure for application like the digital signature or security sensitivity integrity verification likewise. So Whirlpool was developed by Vincent Ridgman and Paulo Berto. So interestingly, they both is also one of the designers who involved in the AES encryption algorithm. So here, the Whirlpool produces 512 bit hash value. So the output size is similar to a SHA-512. Larger hash values generally uh, provide stronger resistance against the collision attacks. So internally, the Whirlpool uses design ideas inspired by the AES block chipper to process the data securely. So the important thing is that AES influenced Whirlpool's internal structure, and choosing a strong modern hash function is very important to maintain data integrity and the trust within the today's digital systems. Then we have very important concept, that is HMAC. So hash function, which is verified data integrity, the message authentication code, which verify both integrity and authenticity using a secret key. So HMAC, hash-based message authentication code, which combine the strength of cryptographic hash function, secret keys, to provide a secure and efficient method for the message authentication. So the HMAC stands for hash-based message authentication code. It is a technique that is used for a cryptographic hash function like SHA-256, SHA-512, and a shared secret key will generate an authentication code. So this authentication code, let me show you the structure. Yeah, so this authentication code will help the receiver to verify that the message has not been modified. The message came from someone who knows the secret key. So we know the mechanism of MACs that provide authentication, right? And the hash function which provide the integrity. So the researchers, they wanted a method that could use existing hash algorithm, and they can add the secret key authentication, and they want to be efficient and secure. So the result was HMAC. The result was HMAC. So the hash functions are designed to process data very quickly. Since the HMAC will use the hash function, it is also fast. Like imagine we are verifying a large file. Instead of performing complex encryption, the HMAC quickly calculate an authentication code that will be using a hash function and a secret key. So this makes it suitable for the real-time applications. So many operating systems and programming languages, they already include secure hash function like SHA-256, SHA-512. So the HMAC that will build on these existing algorithms, where the developers do not need to create an entirely new authentication algorithm. So the HMAC must incorporate a key into the use of the hash algorithm. This is one of the most important difference between the ordinary function. So the message will go to the hash, and the hash value, anyone can calculate the hash. But whereas in the HMAC, the message, then secret key, then HMAC algorithm, then authentication code. So without the secret key, an attacker cannot generate the correct HMAC value. So how it is going to work? So in the step one, the sender has the message and shared secret key. Then in step two, the HMAC will combine the message and the secret key. Then it processes them using a hash function. Am I audible to you all? Students, are you all there? Yeah, thank you. So the HMAC, which is going to provide the integrity first. That means the message has not been modified. Then it will provide the authentication. So the sender will possesses the shared secret key. And thirdly, see, the HMAC does not encrypt the message. If confidentiality is required, the encryption must be used separately. It be used separately. So the HMAC, that means hash-based message authentication code, combine a cryptographic hash function with a shared secret key to generate an authentication code that verify both the integrity and the authenticity of a message. So because it is fast, secure, and built on trusted hash functions, the HMAC is widely used in modern technologies like IPsec, SSH, TLS, and JSON Web Token to protect the digital communications. So then the security of HMAC. See, how secure the HMAC is, the first question it will raise. See, the answer for this, it will depend largely on the strength of the hash function that is used in the HMAC. So the security of HMAC depends on the cryptographic strength of the underlying hash function. This means the HMAC itself is only one part of the system. So the hash function like SHA-256 or SHA-512, which will be the foundation. If the underlying hash function is strong, then the HMAC is also considered strong. If the hash function is weak, the overall security can be reduced. So an attacker may try to do one of these two things. Number one, guess the secret key, or collision attack. So imagine like you are in a classroom with only a small number of students. There is already a surprisingly high chance that two students share the same birthday. Similarly, in cryptography, an attacker tries to find two different messages that produce the same hash value. So a birthday attack takes advantage of probability to search for collision more efficiently than checking every possible message. Even though the birthday attacks are more efficient than exhaustive searches, the modern hash function with sufficiently large output make practical collision attacks extremely difficult. So the MD5, which remains more secure inside the HMAC than when used alone, because the attackers only observe the HMAC output and does not know the secret key. So MD5 alone, when MD5 is used by itself, the researchers have demonstrated practical collision attacks. Therefore, the MD5 is not recommended for security sensitivity hashing because, see, by combining a secure hash function with a secret key, the HMAC remain one of the most trusted technique for protecting the message integrity and the authenticity in the modern digital communications. Now, let us look at the public key encryption. See, so far we have studied all about the symmetric encryption mechanisms where the sender and the receiver, they use the same secret key. But however, we need to understand the major challenge. How do we securely share the secret key? See, this problem led to one of the greatest uh, breakthrough in the cryptography, that is public key encryption. So the most famous public key encryption algorithm is RSA algorithm. RSA means Rivest, Shamed, Edelman. So RSA is a public key encryption algorithm. Unlike the symmetric encryption, the RSA use two different keys instead of only one, and these are the public key and the private key. So this is going to solve the key distribution problem because the public key can be shared openly while the private key will remain secret. So here you can see it was developed. This algorithm was developed by three researchers at the Manchester's Institute of Technology. One, the Ron Rivest, Adi Shamir, and Leonard Adelman. So the algorithm takes their first name, sorry, the name of the first letter of their surname, like Rivers, Shamir, and Adelman. Hence, the RSA was created. So the RSA became one of the most widely used public key encryption algorithm in the entire world. It has been used in securing the websites, digital certificates, then um, securing the email transactions, digital signatures, secure key exchange. So although many modern systems now also use other public key algorithms, for the RSA will remain one of the most important algorithms to understand the biggest difference between RSA and the symmetric encryption, which is the number of keys. So the symmetric encryption, one secret key, both the users will share the same key. The RSA, that is the public key, and anyone can know it. private key, only the owner can know it. So two complete different keys are going to be used. So the public key, where you can see the public key PU, the public key is denoted as PU, and two letters are taken for that, E and N. So the public key consists of E and N. This key is the shared public key. Anyone can use it to encrypt a message. And the private key, as you can see, the private key is mentioned as PR, which is taken consists of D and N. This key is never shared, only the owner is going to know that. So the private key is used to decrypt the message that were encrypted using the machine public key. So if you see here, the formula is mentioned: C equals M power E mod N, M power E mod N. So here the C represents the chipper text, M represents the original message, and D represents the private exponent. The private exponent. Again, you are not expected to perform all these calculations. Okay, so but remember how the formulas are used. Encryption uses the public key, decryption uses the private key. So these two key approach solve the secure key distribution problem, and it is going to form the foundation of many modern security systems, which including secure web communication, digital certificate, and encrypted email also. So then only the intended recipients can decrypt the chipper text, because only the intended recipient possesses the private key. So suppose user A wants to send a confidential message to user B. Now the user B has a public key that is shared with everyone, and also a private key which is kept secretly with him. So now the user A encrypts the message using user B public key. Once encrypted, the message becomes chipper text. Anyone can see the chipper text, but only the user B can decrypt it, because only the user B has the matching private key. That is what provides confidentiality. Then in the stepwise process, if you see, first the user B create two keys. One is public key and another one is private key. Now the user B publish only the public key. Anyone can access it. So user A write the message, and he or she will encrypt it using user B public key, and the chipper text will travel across the internet or any messaging path. So even if an attacker intercept it, they only see unreadable encrypted data. Now the user B receives the chipper text. So he or she will use their private key to recover the original message. So no one else can do this, because no one else has user B private key. So in this way, the RSA is based on difficult mathematical problem involved in very large numbers. When implemented correctly with sufficient large key size, these mathematical problems are extremely difficult to solve. So the second part is that protecting the private key, So in overall, if you see, the effectiveness of RSA is going to depend, not only on the strength of the algorithm, but also on keeping the private keys secure and using RSA as a part of a well-designed secure communication protocol. So yes. So now if you see in the previous slide, if you remember, we discussed about the RSA, which provides the confidentiality by using public key for encryption, private key for decryption. So we will learn another powerful feature of RSA. So RSA is not only used for confidentiality, it can also be used for authentication, data integrity. So this happens when the key are used in the opposite direction. So suppose the user B creates an important document. The user B uses the user B private key to digitally sign the message. Then user A receive the message, the user B digital signature, and now the user A use the user B public key to verify the signature. If the verification is succeeded, then the user A knows that the message was created by someone who possesses user B private key. Since only the user B should have the private key, now the user A gain the confidence that the message came from user B. So this is called as authentication. So here, how does the RSA will help to protect the integrity? See, suppose the user B sent this message, approve project budget, and attacker change it to reject project budget. Now, user A verify the digital signature of using user B public key, the verification fails. Why? Because the message has been changed. Even changing one character will cause the verification to fail, and this provides the data integrity. So the receiver knows the message that has been altered or not altered. See, RSA alone is not going to be enough. A secure system always requires the proper key management, protection of the private key, secure of protocols, trusted digital certificates, and very importantly, a very strong hash function. So please remember, in modern cybersecurity, the RSA and secure hash functions will work together to build the trust and to ensure that the digital information is both confidential and authentic. Confidential and authentic. So here, if you see, the process of generating the key for encryption and decryption is given. So it shows clearly that how the RSA keys are generated, how the encryption is working, how the decryption is working, and a complete numerical example is given here. Okay. So if you see, first, we want to select two primary numbers. So we need to choose two different primary numbers. And in the slide, if you see, they have given P and Q. Both numbers must be prime, different from each other. And in real world RSA, these primary numbers are extremely large, often hundreds of digits long also. Why only the prime numbers? See, the prime numbers have special mathematical properties. So the RSA security depends on the fact that multiplying two large prime numbers is easy, but finding those original prime numbers from the product is extremely difficult. And this difficult problem helps to keep the RSA secure. Okay. And in the next step, we will calculate the n value. Then we will calculate the Euler's or totient, and we will choose the public exponent E, and then we will calculate the private exponent D, and then we will create the public key as well as the private key. So the steps will follow like this: choose two prime numbers, then calculate n, then calculate totient of n, and choose E, then calculate D, then generate the public key and private key. So this is the complete case of key generation. Suppose Encryption uses the formula what? C equals m to the power of C mod n. So M is plain text, C is ciphertext, and E is public key value, and N is the public key value. So the encryption always use the public key. Then again, we have the decryption to use, that is the private key. So for example, in this example, if you see, the original message is represented by 88, that is the plain text. Okay. Now, if you see PU, which is given as 7 and 187, which means E is 7 and N is 187. So using the RSA encryption formula, 88 becomes 11. So the plain text equals 88. After encrypted, the chipper text is 11. Now the receiver has PR of 23, 187. This means D is 23, and now decrypt the 11 using the private key. So the result becomes 88, exactly the original message. So it followed all the RSA process with 8 steps, and it has successfully converted the plain text into the chipper text and chipper text into the plain text. So then this elegant two-key approach is what makes the RSA one of the most influent and widely used public key crypto systems in the modern cyber security. Now, the RSA crypto system security aspects, let us see. So far we learned how the RSA generate the public and private key, how the RSA perform encryption and decryption, how the RSA can also provide authentication through the digital signatures, all these things. Now, the thing is that we need to ask one question: can RSA be attacked or not? Yes, like every cryptographic system, the RSA also can be targeted by different types of attacks. However, when you have a well-designed RSA system with a strong key and proper implementation, which remains secure against all these attacks. So understanding attacks will help the security professionals to design stronger systems. When we think of it, the way, if you know how a thief might try to enter a house, you can build better locks and security systems. Similarly, learning about RSA attacks will help us to understand how to protect the RSA implementations. So the first attack here, if you see, it is listed as brute force attack. So this attack attempts to guess the private key by trying every possible key. Then the second attack is mathematical attack. So remember, like how the RSA begins. We select the two primary numbers, right? Then we will calculate n value. The public value n is known. The attacker tries to discover the p and q. So this process is called as integer factorization. Remember, integer factorization. So multiplying two large primary numbers is easy, but finding the original prime number from their product is extremely difficult, and that mathematical difficulty is what protected the RSA crypto system. So we use sufficiently large primary numbers. Modern RSA implementation use very large prime to make the factorization infeasible. And the third attack is chosen ciphertext attack. So in this attack, the attacker deliberately submit specially crafted ciphertext to learn the information about the decryption process. So the goal is, it is not simply to read one message, but to exploit the weaknesses in the way the RSA is implemented. So the modern RSA system includes secure padding scheme like OAP to help defend against such ciphertext attacks and all. And the fourth attack is timing attack. The fourth attack is what? Timing attack. So this attack does not break the RSA mathematics. Instead, it studies how long the computer take to perform the decryption. So if the pattern repeats consistently, an attacker may gradually learn the information about the private key, about the private key. So the first reason is it comes from an unexpected direction. So most people expect the attacks to focus on mathematics. Instead, the attacker studies the computer's behavior. And the second reason is it is a chipper text only attack. So the attacker does not need the original plain text. Only observing encrypted messages and execution times may provide useful information that makes this attack particularly interesting. So please remember that in practice, the RSA algorithm itself will remain secure when appropriate key size are used. Many real-world attacks target poor implementation rather than the underlying mathematics. Therefore, the secure systems will rely on multiple layers of protection, including the strong key generation, secure padding techniques, then constant time implementations, and also the careful software engineering to resist both mathematical and side channel attacks and all. So by using large keys, secure protocols, proper padding, and side channel resistant implementations, the RSA continue to provide strong security for modern digital communications. So now the countermeasures are very important. See, the timing attack. A timing attack does not try to break the RSA mathematics, right? Instead, the attacker carefully measure how long the computer take to perform RSA operation. So the small differences in the processing time may reveal information about the private key. Now, the important thing is that how can we defend against the timing attack? So let us understand that. A security technique that is used to prevent or reduce the success of an attack is the countermeasure. So when you think of it like installing better lock, security cameras, alarm system to protect a house, similarly in cryptography, the system can use the countermeasures to protect against the attacks. So the first defense mechanism is constant exponentiation time. So normally some RSA operation may finish slightly faster than others. An attacker may notice this timing difference. Instead, the computer is designed so that every RSA operation take approximately the same amount of time. Then the second defense mechanism is random delay. So instead of always responding immediately, the computer intentionally wait for a small random amount of time before returning the result. And then the third thing is that blinding. So here the blinding is one of the most effective technique against the timing attacks. So before performing the RSA calculations, the system temporarily modify the chipper text by combining it with a random value. Only then does it perform the RSA operation. So after the calculation, the effect of the random value will be removed and the correct result is going to be recovered. The correct result is going to be recovered. So the strong cryptographic will depends not only on secure algorithms but also on careful implementation that prevent the attackers from learning the secrets through the side channels and all. Then we have another very important public key technique. Unlike the RSA, the Diffie-Hellman is not mainly used to encrypt the message. Instead, its primary purpose is securely creating a shared secret key between two parties over an insecure network, and that is called Diffie-Hellman Key Exchange. So the Diffie-Hellman Key Exchange is a cryptographic protocol that allow two people who have never met before to securely create the same secret key over the internet. So it does not send the secret key across the network. Instead, both the users independently calculate the same secret key. So the Diffie-Hellman key will exchange that was proposed in 1976 by two researchers, Whitefield Diffie and Martin Hellman. So this was one of the first practical public key technique that is ever published. So it becomes to know that James Ellis and Clifford Cock and Macklem Wilson at the UK's CEGS that has independently developed similar public key concept earlier, but their work remained classified for many years. So imagine, for example, there are two people who want to communicate securely. They need to share a secret key, but they have never met before. How can they exchange that key safely over the internet? If they simply send the key, an attacker could intercept it. So the Diffie-Hellman solved this um, problem. It allows both the user to create the same secret key without ever transmitting the key itself. Like, let me show you one real life analogy. Here you can see, let us say there is a user A and user B. Now the same empty paint bucket they have, and they both have same public paint color. Everyone, including an attacker, so can see the public paint color. Now user A secretly mix their own private color into the bucket, and user B secretly mix their own private color into the another bucket. They exchange only the mixed color. After one more private mixing step, both end up with exactly the same final paint color. The attacker saw everything exchanged but cannot recreate the final secret color because the private colors were never shared. So that final secret color is like the shared secret key in Diffie-Hellman. So first, user A and user B agree on some public transformation. Everyone can know this information. And in step 2, user A choose a secret number and user B also choose a secret number. These numbers will remain private. So in step 3, each person will perform a mathematical calculation using the public information and their own private number. They exchange only the calculated result. Now each person will perform another calculation. Surprisingly, both calculate exactly the same secret key. Now what will happen? The shared secret key itself is never transmitted. So the result will be not, I mean, it is going to be succeeded, the transmission, and nothing is going to be hacked. So in many modern systems, the epic curve Diffie-Hellman is preferred because it provide the comparable security with similar key size and improved efficiency. So this security security key exchange from the foundation of many modern communication systems, enabling the fast and secure symmetric encryption for protecting the digital information. And then man in the middle attack. So it is one of the greatest advantage in that two people can establish a shared secret key without sending the key itself over the network. Now we may think that if the secret key is never transmitted, is the Diffie-Hellman completely secure? The answer is not by itself, because without proper authentication, the Diffie-Hellman is vulnerable to a very important attack that is called man in the middle attack. Let us understand how it is going to happen. Okay. First of all, what is this a man in the middle attack? An attacker secretly intercept and relay the communication between two parties while pretending to each that they are communicating directly. Okay. So in the first step, the Darth creates two key pairs. The Darth will generate two separate private key and two corresponding public key. Why two? Because Darth wants to establish one secure connection with user A, another secure connection with user B. So the Darth pretend to be user B when talking to user A and user A when talking to user B. So the user A sends their public Diffie-Hellman value to user B, but the Darth intercept it before it reaches the user B. instead of forwarding user A public value, the Darth will send their own public value to user B. So now what will happen? So the user B receive Darth public value. So user B has no idea what happened in between. So the user B believe the value came from user A. And in the next step, the step 4, the user B now calculate a shared secret. However, it is not shared with user A. Instead, the user B unknowingly established a shared key with the Darth. So in step 5, now the user B send their own public value to user A. Again, the Darth intercepted. Instead of forwarding user B public key value, the Darth will send another one of his own public value to user A. So now user A believe it came from user B, and in step 7, now user A calculate a shared secret, but again it is not shared with user B. Instead, user A unknowingly establish a shared key with the Darth. So what will happen? Instead of one shared secret, there are now two different secret keys. So user A and user B never share the same key. Instead, the Darth shared one key with user A, another key with user B. So what will happen next? Now the user B never realized the message was intercepted. Similarly, the message traveling from user B to user A are also intercepted. Now, meanwhile, user A and user B continue believing that they are communicating securely. So, this is why the secure key exchange must always be combined with strong authentication mechanism where it will ensure not only secure communication but also trusted identities. So now let us see. There are two other important public key algorithms that are widely used in modern cybersecurity. One is the digital signature standard and applied chaos cryptography. So these algorithms were developed to solve different security needs. Okay, so different applications have different requirements. Some systems require secure encryption. Others may require the fast digital signature, or even others require strong security with limited computer power, such as smartphones and even IoT devices. So therefore, different public key algorithms have been developed for different purposes. Number one, the digital signature standards. Let me show you the process, how it helps. So the first algorithm is digital signature standard. We call it as DSS. So the DSS became a US government standard under FIPS Pub 186. It was first published in 1991 and later it is revised in 1993 and 1996. So the most important point here is the DSS is designed for digital signature. Its purpose is to verify the sender's identity, ensure the data integrity, and support the non-repudiation. So the DSS cannot be used for encryption. This is an important thing. Unlike the RSA, which can perform both encryption and digital signature, the DSS is designed only for digital signatures. Digital signatures. So it does not encrypt confidential information. So the DSS use SHA-1 in its original design. So a digital signature is generally created by computing a secure hash of the message and signing that hash using the signature algorithm. So this is one way, and we have the random numbers. See the random numbers. Why are the random numbers so important in cybersecurity? If you see, the answer is very simple. Almost every security system depends on generating the unpredictable numbers. So these numbers are used to create encryption key, initialization vector, the session key, one-time password, random challenges in authentication protocol. So if these numbers are predictable, the entire security system will become vulnerable. So a random number is a value that cannot be predicted before it is going to be generated. So every new number should appear independent from the previous one. So suppose there is a system which generates like 7, 42, 91, 15, 63. There should be no obvious pattern. If someone can predict the next number, then the numbers are not suitable for cryptography. First thing, the randomness. So this means the generated number should pass the statistical test. Two important properties are going to be checked. Every possible number should have an equal chance of appearing. Equal chance of appearing. Then the second thing is that independence. So this means the next random number should not depend on the previous one. Then the second requirement is unpredictability. So successive value should not be related to the previous value. Though this is one of the most important requirement in cryptography. Even if an attacker observes many previous random numbers, they should not be able to predict the next one. And then there are two main types of random numbers. One is TRNG, physical unpredictable events like radiation, gas discharge, or leaky capacitors. So the modern processors may also include dedicated hardware random number generators and the pseudo random numbers PRNG, where the algorithms, like a computer starts with an initial value called a seed, the algorithm then generates a long sequence of numbers and all. So in overall, if you see, the random numbers will generate in one of the foundations of modern cybersecurity, and strong encryption algorithms like AES, RSA, Diffie-Hellman, they are all relying on unpredictable keys to remain secure. In practice, the modern operating system will combine the hardware randomness with the cryptographically secure pseudo random number generator and to produce the high quality random values that are suitable for security applications. So secure cryptography system which depends on high quality random numbers. Good random numbers must be statistically random, unpredictable, and independent, while the true random numbers come from physical sources. Modern software and commonly uses the cryptographically secure pseudo-random number generator to efficiently produce the secure random value. So with this, we completed the module 2. So students, I kindly request every one of you to complete the discussion board. So the module 3 and module 4 will be available to you all as a recording, and day after tomorrow you all will receive the assignment 1. So your assignment 1 will cover the module 1, module 2, module 3, and module 4. So please excuse that we have started late. Due to the assignment of classes to me, it was delayed, and I tried my best to cover the content in the week classes itself. But by next week onwards, as I'm going to provide now the module 3 and module 4 as a recording, so from next week we will be on track. So that means in the next class we are going to start the module 5 as per the schedule, and before that we have module 3 and module 4 that will be available as a recording to you all. Okay, is it clear? Okay, so thank you all for joining today's session, and the attendance will be posted on the banner system, but still the student details are not yet reflected, so I'm waiting for that. So once it is reflected on the banner system, surely you all will get an update of that. And also I have shared all the PPTs related to the course through the course message, so please download that and start studying. Okay, so thank you. If you have any queries, please feel free to ask, or else if you want to leave, yes, you're free to leave. Have a nice day. Thank you. Yes, yes, sure. As soon as I upload the recordings regarding the module 3 and module 4, I will surely intimate you all through the announcement. Okay, by tomorrow.